9 o'clock classes are canceled, which means your 8 o'clock class will be shortened, okay? It'll end at 9, and then everybody heads to the gym on the Birmingham West campus. That's the Arthur Shores Fine Arts Building, and that's our gymnasium. That makes a lot of sense. Okay, so then we have that, and it usually runs more than an hour, and hopefully less than 2 hours. So you should when do classes usually start? Resume again. I think 12:30 is the normal start time. So certainly the 12:30 classes should start. I don't know if you can start the 11 o'clocks or not. I kind of doubt it. But check with your instructor to see if you're having class. You're 9:30 or 11. 9:30 certainly is canceled. Check and see if the 11. Now, it could be, if you have an adjunct instructor that is not going, doesn't have to go, and most of the class doesn't have to go, they may actually be holding class. I doubt it.
Because my 8 a.m. class is canceled.
Really?
Yeah, he has to go.
Okay. What is that?
We don't meet that day.
What?
It's Mr. West.
Mr. West. Okay. Well.
He says it's just online class.
Yeah. Well, I have an 8 o'clock class, and we're going until 9 because that's when they officially cancel. Yeah. And I can get over there in 30 minutes usually. So, but it doesn't start till 10, so I wouldn't sweat it if I don't get there until 9:50. But they want us there earlier than that. Okay. Well, I had thought this had opened. Let's see if it has. Yes, there it is. Okay. So let's start this from the current slide. And then I'll... Okay. Here we go. They only showed example 1 on the slide set. And we have done example 2, 3, and 4. Now we're doing example 5. Now example 5, let me get my pen set up. Well, first I should ask this. Any questions on anything we've done so far? Okay. Any questions? Okay. Example 5 is one of these that says, see larsoncalculus.com for an interactive version of this type of example. So if you don't like or understand or follow what I'm saying on this, by all means go to larsoncalculus.com and get a different view. Even if you like what I'm doing, go on and get a different view of it. Okay? It says, analyze and sketch the graph of f of x is equal to x to the 4th minus 12x cubed plus 48x squared plus or minus 64x. Okay? It says analyze and sketch the graph of. Okay? Now, I can't remember if we did this before. I know early on, I think I did it. But let's start at the very beginning. Can anyone tell me just basically something about how that graph is going to look? The graph is just conceptually. Something about how it's going to look. Hint, leading term. What does that tell you? Okay, it could have up to 4 zeros. Is that what you're saying? 4 solutions? It could have up to 4. May not have 4, but it could have up to 4. Which also means it will have up to 3 changes of direction. May not have 3, but it could have up to that. It's certainly true. Anything else? What's happening toward infinity? Words. Say again? It's what? Okay, you think this one is going to 0 as you go to negative infinity or positive infinity. This is a polynomial function. Polynomial functions never head to 0. Rational functions may. Okay? Polynomial functions no. They're always going to some infinity somewhere. Because if x is going to an infinity, either positive or negative, you know x to the 4th is They're even faster, right? So, where do you think this one's heading? Up and up. Okay. At the negative infinity is going up, positive infinity is going up. Why? Because x to the fourth is an even power. It's always going to be positive. And the coefficient is positive, meaning it will be positive. Okay? So we have an idea right now. It's on the up and up, this way. It could have up to 4 zeros and up to 3 changes of direction. So that's what we can know just looking at it. Okay? Now, what's another thing you might note? Normally, fourth degree polynomials, I don't know how to go about factoring, but this one, I do know something. What do you notice here? Yes, for sure, we can factor out an x. This will be x times x cubed minus 12x, you tell me. 12 squared plus 48x minus 64. Okay? Yay, I like it. Okay? Now, that tells you something else. One of those potentially 4 zeros is going to be zero. X equals 0 is going to be a 0 for the function. If x equals 0 is what would be the y value for that one? X equals 0? 0. Okay, guess what? We've just found our one x-intercept and our only y-intercept. 0, 0. That is an intercept. So we know that. We know it's on the up and up. We know x equals 0 is a 0. Now, what we don't know is whether that's a maximum, a minimum, or a neither. Okay? It could be, oh, it doesn't have to be a maximum. We'll get there later. Okay? Is there anything else we can tell just by looking at this? Okay, because it says analyze, sketch and analyze the graph. I would be really tempted to try to do a factoring by grouping here. It looks like it has potential. May not work, but let's see if it might. Okay? If we group these two and those two together, what do we get? The x is a factor. What does this give us? Okay? This will factor out an x squared times 12. Okay? Plus, and what can we factor out there? I know we can do a 4. No, we can do an 8. I think we can probably even do a 16, can't we? Yeah, and that's not going to help us much, is it? 16 times 3x minus 4. Nope, sorry, no factoring by grouping here. But it was worth a shot, right? Just to make sure that there wasn't, okay? Worth the effort, but not there. Close, but no cigars. Okay. So I guess we've done all we can from pre-calculus algebra days. Can't think of anything else we could do. Oh, let me do this too. That wasn't helpful, so let's get rid of it. Now we may actually want to go back to the original function here. Because what are we going to do now? You've used up all your pre-calculus stuff that I can think of using anyway. Let's go to calculus stuff. What might be a thing you could do? Take a derivative. I think it's easier to take a derivative of the first one. So let's do that. That means that f prime of x is equal to help me. Say again? I wouldn't use that one just because then you're going to have to use the product rule. Let's just use the original. Okay? That's just power, polynomial. It's just easy. Do it. What would you get? 4x cubed. You don't have to use any particular thing. You use whatever's easiest. Okay, next. Minus, say again, 36 x squared. Got it. Plus 96 x minus 64. All right. Now, why would we want to take a derivative anyway, except it's a Cal 1 class? That's what you do, right? Okay, find the zeros of that first derivative. What will they give us? You what? Not inflection, critical points. Critical values, okay? The critical values, either where that's equal to 0 or whether it doesn't exist. Guess what? This is a polynomial function that exists everywhere. First derivative exists everywhere, so you don't have to worry about where it doesn't exist, just where it's equal to 0. So this thing we do want to set equal to 0, and what would be the first thing you would do then? Same thing we tried before. Yeah, actually we did it before. Yes, and what can you factor? Simplest. First step. 4. Well, I sure hope we can anyway, because those numbers are way too big. What does that leave us with? X cubed. Help me, help me. Minus, what do you say? 9x squared. Is plus, isn't it? Is it 24? That sounds right. X minus 16. And that's equal to 0. Okay? Now, since we've set it equal to 0, I'm going to do something that's not very nice, but hopefully you'll see. I'm just going to divide out my 4. What good is that doing? 4 is never equal to 0, so therefore, let's just divide it out. Divide both sides by 4, and this thing disappears. Okay? Like that. All right. Now, you might try factoring by grouping again, but I would say probably not. Why? Factoring by grouping is the same type thing that we could have seen here. This number here is 12 times this one with plus or minus the sign. The signs are good, but this number is 12 times that, and that one's not 12 times that one. So you should have known factoring by grouping wasn't going to work there, even if Elijah did come in, okay? And this one I'll tell you again, factoring by grouping is not going to work because Diamond came in, okay? No, that's not the reason. There had to be some reason, okay. Okay. And here's why. Because the second factor here is 9 times the first. This one, the first factor is bigger than the second. So factoring by grouping is not going to help in that. So what do we do to find those zeros? Okay. And since I wiped out the 4, let me go on and wipe it out completely. Hopefully you'll follow this even if you didn't see when you came in. It just looks messy to have all that in there. Okay. How do we go about finding zeros of a big polynomial like that? Do you remember any of the techniques from your pre-calculus? And we could have done some of these with this one too, but I wasn't as interested in the zeros. Hopefully we'll find these later. But let's try. What are some of the techniques for finding zeros in a higher order polynomial like that? Oh, how soon we forget. Say again?
I would say the ABC method, but it's one.
Okay, quadratics are easy. This is higher order, okay? Now, so here's one. Hopefully this will ring some bells. Rational zeros test. Oh, blank faces, okay? Okay. What you do there is look at the ratio of the constant term to the leading coefficient. And that's a 16 to 1. And you break that down into all the possible factors. So what's all the, and that's called your P over Q is 16 over 1. Okay? So you do all the possible factors, P over Q, and what's all the possible factors of 16? Name them. Plus or minus 1, plus or minus 2, plus or minus 4, plus or minus 8, and plus or minus 16. Okay? Over your possible factorizations of your leading coefficient. 1. That's just plus or minus 1, so we don't even need to write that down. Okay? Now, then, what do we do with that? We start testing them. Okay? And the easiest one to test is plus 1. Okay? And the way to test that, if you put a 1 in here, then all you have is your coefficients. So just add the coefficients together and see what you get. When you add these two, you get 25. Add these two, you get minus 25. Ding, ding, ding. There's a 0 right there. So x equal 1 is a 0. We already got x equal 0 is a 0. Now we have x equal 1 is a 0. Okay? So zeros, x equal 1, x equals 0. And by the way, that point is 0, well, all these are. And x equal 1. Okay, now, what do we do with that? We know it's a 0, but we still have to do a synthetic division. 1 into, and then you write those coefficients down. What are they? 1 minus 9, 24, minus 16. And then my little rule is skip a line, draw a line, okay? And then bring down the 1, and then you do what? Multiply. And what does that give you? 1. Then you add, and that gives you negative 8. Then you multiply, and that gives you negative 8. And then you add, and that gives you, and then you, and that gives you, and then it gives you, ding, ding, ding. We knew that was going to happen because we knew it was a 0, right? But what's the upside of this? We just did something we already knew, but now we've got the other factor. Right? Your quotient is a factor. And what does that stand for? What do you put back in? With synthetic division, you take out the variable, so when you get the answer, you put it back in. And what do you have there? Say again? Yeah, that's the coefficient. What's the variable? X squared. Next. Next. That's for the 1. Next coefficient is negative 8 what? X plus 16. Okay. Now, why didn't I continue doing synthetic division? I could have, but guess what? Just like Elijah said, if that was a 3-term, we can factor it. Or use quadratic formula. There's lots of things we can do when you get it down to quadratic. So once you do your synthetic division, once you get it to 3 digit quotient, three number quotient, three coefficient quotient. Write that down. Now, let's see if we can factor that. Anyone want to hazard a guess? X minus what? Minus what? I couldn't hear. Minus 4 times X minus, say again? 2, 4, 6, 8. Who do we appreciate? Okay. Minus 4. Okay. Does that work? It sure seems like it should. Let's see if it does. 4. X times X is X squared. Minus 4X is minus 8X. Minus 4 times minus 4 plus 16. Yes, it works. So there are other 2 zeros for your first derivative. Okay? X equal, sorry. I messed up. I'm mixing them up here. Okay. All right. Sorry about that. The zeros for the function, all we know is X equals 0 now. There's probably some more, up to 4 of them. The zeros for your first derivative, though, are X equal 1 and X equal 4. But X equal 4 is what we call a multiple or double zero, multiplicity of 2. Now this is for the first derivative, okay? So those are our only 2 critical points now. I'm expecting X equal 1 to be sort of normal. I'm kind of expecting X equals 4 to be a little, it could be strange because you have a multiplicity of 2. So we have critical points. Let's figure out what the Y value is for those critical points. We already know the Y value of that 0 is, of course, 0, 0. Okay? Let's do the Y value for these. F of 1 would, we haven't done that. F of 1 is just adding your coefficients together. And again, let's add your positives, 49, your negatives, minus 78, is that right? The 76. And 76 minus 49 is 27. Is that right? Okay. And that's a negative 27. So, so that would be 1, negative 27. There is a critical point. Now, we don't know if it's a maximum, a minimum, or a neither. Okay, we haven't tested that yet. How about that second one, X equal 4? Ooh, that's going to be harder to plug in. I think I'll need a calculator help with this one. So pull out your calculators and see what you might check your other one. That's a weird seeming number there. Nope, it's right. Okay. I looked in the book. Okay. Plug in F of 4. So it's 4 to the 4th minus 12 times 4 cubed plus 48 times 4 squared minus 64 times 4. Four to the 4th is, goodness gracious, what is that? 128 maybe? 4 squared is 16, times 4 is 64, times 4 is, no, ends with a 6. 256, I think, maybe. I don't know. but that's just the first term. You got calculators, plug them in. So got a 0. Oh, how nice. Okay. So our first derivative, our critical point, is also a 0 of the polynomial. That's interesting, huh? So we now have another 0 up here for 0 of the polynomial, and we have a critical value point of 4, 0. Okay? All right. Now, what might we do next? This is a Calculus 1 class. So what might? Say again? Second derivative. Let's do it. And we'll use that first derivative to take our second derivative. F double prime of x is equal to. Now, don't go back to the one that we divided out the 4. That's still part of the second derivative. So go back to the real second derivative. Okay? What does that give us? 12x squared. What sign? Minus 72x plus 96. Now, what might we want to do with that? Say again? Points of inflection. Exactly. And what will, how will we find those? Set this equal to 0. All right. Or where it doesn't exist, but this is a good polynomial function, it exists everywhere, so we don't have to worry about that one. What would be your first step here? Factor out the 12. I don't like the 12 that much. It's too big a number. What do we have left? X squared minus 6x plus 8. All right. Equals 0. Okay, I'll get rid of the 12. I'll divide it away. Okay. Now we see, is that factorable? I kind of hope so. What would that be? Help me, help me. That looks like a winner to me. X times x is x squared. X times minus 4 is minus 4x. Minus 2x is minus 6x plus 8. Yes, that works. So what does that give us? Our 2 points of interest.
2 and 4.
X equal 2 and x equal 4. Oh my goodness. Hear that? 4, 0 is a 0 for the function. It's a critical point for the function, and it's could be a point of inflection. Okay? Wow, it's doing triple duty here. Okay. And it's a double multiplicity 2 on that first derivative, by the way. Which, remember I said we're sort of suspicious of that one, and we're ready to go with it then. All right, now, what does that tell us? Okay? At x equal 2, you have a 0 for your point of your second derivative. Okay? Now, probably what we ought to do, now we haven't found all the zeros of the function yet. I feel kind of bad about that. So we probably need to go back and do that one as well, right? We know x equals 0 is 1 from here. We found out x equal 4 is 1. So with this part here, this factor here, let's go back to that. We tried factoring by grouping, it didn't work. So we'll do x cubed minus 12x squared plus 48x minus 64. Okay? Now, again, let's do our rational zeros test. The P over Q here will be all the possible factorizations of 64. And what would they be? Plus and minus 1. I should have left more room. Next. Plus or minus 4. 8. 16. 32. 64. And guess what? The denominator is plus or minus 1. So we don't need a denominator. There they are. Okay? We already know the plus 4 is going to work. Okay? Easy to check to see it. Oh, let's just use it. Since we know it, let's use it.
But if we had a 2 there for our first, like if it was 2x cubed, we would have to do 1 and 2.
Yes. For your denominator. Exactly. I was just relishing in the fact it wasn't. Okay. All right. What I'm going to do is erase this one, because we already found the result for that one. I didn't need to erase the 1. I think we've used this all we can. So let's go on and do our synthetic division with this one. And we're going to use the one we know already. We know 4 is a 0. Normally I wouldn't start there, but I am this one because we know it already. Why not? Okay? Your coefficients are Coefficients are 1,
12,
negative 12, 48,
negative
and negative 64. Okay? Now, we've already added those together, remember? And we came out they weren't equal. Okay. So 1 wouldn't have worked anyway. 4 we know will work, so let's try it. Okay? I already drew a line, skipped a line, draw a line, brought down the 1. You tell me what to do next. 4. Negative 8. A little louder. Negative 32. 16. 64. 0. Ding, ding, ding. We knew that was going to be the case, didn't we? Okay? That 64 is indeed, that the remainder should be 0 because we knew that was going to be a 0. What does that leave us with here? That looks awfully familiar, doesn't it? Same thing we had before. What does that represent? X squared minus 8x plus 16. Which we already know what that factors as, right? X equal, well, let's factor it. X minus 4 minus 4. Okay. Whoa. This is amazing, isn't it? Not really, but it is kind of. Okay. That means our only 0 for the function is a triple 0. I mean, besides x equals 0, is a triple 0 at 4. Multiplicity of 3. X equal 4, x equal 4, x equal 4. Okay? So it only has 2 zeros, 0 and 4. 4 is a triple 0. Okay? And it's a critical point, meaning you have a 0 tangent line there. And it's a point of inflection. Okay? So what does this tell us? Okay? A bunch of stuff, really. So let's evaluate first this. What is we already know 0, 0 is an intercept. Okay? It's the solution. Okay? And the first derivative at 0, 0, x equals 0, is minus 64, right? First derivative, minus 64. Whoa! That is sloping down really, really fast, right? Negative 64 slope. Wow! Almost vertical. Not quite. Okay? So that's one thing it tells us. Second derivative is this. Second derivative is 96, meaning it's concave up. So, I'm going to try to squeeze in my graph here, okay? Okay? 0, 0 is a 0 for the function. We already determined this has to be coming from way up north, right? Positive in both directions, right? So I'd say this is coming down really, really fast right here. Slope of negative 64, but it's coming down with a concave up, right? Because, so it's doing like this, okay? And here's highlight. Okay. So it has to be concave up there, okay? Now, the next value of interest for us here is x equal 1. That's where we have a slope of 0. First derivative is equal to 0. Okay? And so at 1, and that's 1 negative 27, so it's way, way down south here. Let's just say that's negative 27 down here. Coming down, concave down here until it gets there. And at 1, let's plug in, we know the first derivative is 0 there. What's the second derivative at 1? When x equals 1. Plug that in here, and what do you get? I really don't care about the number. I want to know the sign.
Positive.
Very positive. Meaning still concave up, right? Concave up at 0, concave up there. So that means this one is a minimum. It is a local minimum. Okay? So 1 negative 27 is a local minimum. Okay? So somewhere there. Okay? The next value is our 4, 0. Okay, that's 1, 2, 3, 4. 4, 0 is a 0 of the function. It's the first derivative equal to 0, and the second derivative equals 0, which means we can't tell what's going on there. So what we need to do is evaluate it. Okay, that's at 4. Let's do it 5. Okay, I got a suggestion for you. We don't have to do 3. Do you think? I don't think we need to evaluate 3. It's got to be negative. Okay? And by the way, oh yeah, well, we'll have to skip 2. X equal 2. That's another point of inflection. Okay? So we do need to evaluate at 3 because we need to know, we know it's concave up until it gets to 2. What happens at 2? That's either supportive inflection, which means the second derivative is 0, but it doesn't tell us whether it changes concavity or not. I think it will, okay? So let's evaluate the second derivative at 3. What's the second derivative at 3? Roughly. 3 squared is?
Positive.
Okay, you say it's positive? 3 squared is 9 times 12 is 108. 3 times and 108 and 96 will add to be 204. Is that right? Okay, 204. 72 times 3 is more than 210. So it's negative there. So we know at 2, we do have it as concave up here, concave down there. So it must be concave down coming in there. So at x equal 2, we have a point of inflection going from concave up to concave down. Okay? And it has to reach 0 there. Okay? We don't know what happens there. So let's take a value of the function here at x equals 5. Whoa, calculator time. 5 to the 4th minus 12 times 5 cubed. Am I going too fast? 5 to the 4th minus 12 times 5 cubed plus 48 times 25 minus 64 times 5. I could have done all this. 625 minus 12 times 125 plus 4 times 25, 48 times 25 minus 64 times 5 equals?
5.
Positive 5. Okay? So the function here is plus 5. Okay? Guess what, team? You have a first derivative of 0, a second derivative of 0, so it's going up like that, and I bet you it's concave up from there on. So let's make sure first that it's increasing. So we'll plug in 5 there at your first derivative. I bet you it's going to be positive. Let's see. 4 times 125 minus 36 times 25 plus 96 times 5 minus 64. Is that positive? I think so. Okay. Second derivative there. I'm thinking positive. Let's see if it is. 12 times 25, that's something like 300, isn't it? Minus 72 times 5, which is greater than 300, but then not enough greater than plus 6 is going to be positive. So sure enough, it's going up from there. All right, I think we have basically what the function looks like. Concave up, and going to positive infinity. Remember we said that. It's got to be on the up and up. Okay? So, fits there. Concave up here, with very steep slope here. Okay? And coming down here, a relative minimum there. Chaston is here. Still concave up, but at x equal 2, it switches concavity from positive to negative and comes in at here. But the 0, a critical value, and a point of inflection here, potential point of inflection. And sure enough, it's concave down here, concave up there, and positive slope there, and going to very large numbers. Got it. Okay? You see how that works? All right. If you look at your text, you'll see all that. And they mention several other things. The domain of the function, so this is a polynomial function, all real numbers. Okay? Range. Now that we graphed it, we see it never goes, you know it's on the up and up, so it has to have a minimum somewhere. That minimum happens to be negative 27. So negative 27, was that 27? I think it was. Negative 27 is positive infinity. Got it. Okay? X-intercept, 0, 0, and 4, 0. Those are the only ones we had. Y-intercept, only that one, 0, 0. You can't have more than one Y-intercept. Okay? Vertical asymptotes, none. There are no places where your denominators are 0. There aren't any denominators, okay? Horizontal asymptote, none, because this is a polynomial function. Your end behavior is negative, is never approaching a horizontal line. Always going toward an infinity. So no horizontal asymptotes. Symmetry, none. How can you tell that? Look at the function. Even, odd, no way that's going to be symmetric about anything. Okay? End behavior, we already said that. Up and up, going to positive infinity when x is going to negative infinity, or positive infinity, the y is going to positive infinity in both cases. First derivatives, we calculated that, and we found out that it had, when we factored it, we didn't really factor it, but ultimately we did, is we factored out the 4, okay, times x minus 1 times x minus 4 squared, okay. We didn't write it the way they did, but we found that was the first derivative. Second derivative, when we did that, we found out it was 12 times x minus 2 times x minus 4, okay. They have it work. Critical numbers, 1 and 4. Possible points of inflection, 2 and 4. And again, we said the zeros were 0 and 4. And they did a bunch of test intervals. We kind of did. We looked over here negative and said, we knew that had to be, knew with a slope that was really, really negative, it had to be coming from positive on this side to negative on this side, because it was 0, 0. We tested concavity, and it was concave up. concave up all the way down to here, past here, until we got to our first point of inflection. And it was a point of inflection. Change concavity there. And then we were concave down here, concave up there, so we had that. So we really we didn't look at any particular value over here, we just looked in general what was going on here. We looked at one, we tested concativity here. It was positive, positive, so we didn't have to check anything else. We knew it was concave up here, so there's no real reason to check anything else there. We have a possible point of inflection here, so we did check over here to make sure it was concave down there. So we did use that test period value, and we used the test value here to see which way the function was going, and which way the concativity was going, and which way the first derivative, the tangent lines were going. So yeah, we probably should have used the -1 here to evaluate the function, the derivative, and the concativity. Use this one, but we could tell looking at it what those were. Okay, we did use this to get what the function value. Well, we didn't actually physically do that, but we did do what first derivative was. Well, we knew it had to be positive. You can't get from here to there without it being a positive slope. So we really didn't do that. And then from there on, it was positive from then on out. Because you have no more critical numbers or points of inflection. Okay. So they did a lot more test intervals than we did. They did negative infinity to 1. Oh, they should have done it to 0. Shame on them. And 1 to 2, and 2 to 4, and 4 to positive infinity. They really should have done one up here too, but we didn't either. If you're going to do them all. Okay. And then you see that the first derivative, the function value from negative infinity to 0 was always positive. Okay? From 0 to 1 was always negative. Okay? Your first derivative from negative infinity to 0 was negative, and your second derivative was positive. And then from 0 to 1, the function value is negative, the first derivative is negative, and the second derivative positive. At 1, the value was negative 27, the first derivative was 0, the second derivative was positive. That means it had to be a relative minimum. Okay? From 1 to 2, the function value was negative, the first derivative was positive, and the second derivative was positive. From 1 to 2, is that right? Yeah, 1 to 2. So that means you still concave up there. At x equal 2, your value, and that's what we didn't calculate, was negative 16, so it's still negative. The first derivative was positive, sloping upward, and you had a change of second derivative, 0. That is indeed a point of inflection. Okay? From 2 to 4, your value of the function was still negative. The first derivative was positive, second derivative negative, so there you're concave down. Increasing but concave down. X equal 4, everything was 0. So you know you have a 0 there, you know you have a critical point there, and a possible point of inflection, but you don't know that for sure until you check on the other side. From 4 to infinity, the function was positive, the first derivative was positive, the second derivative was positive, meaning, yeah, that was a point of inflection here. You changed that. It wasn't like it came in this and left that way, or went like this somehow, some sort of weird thing there. No, it was a change of direction, a change of concativity, which means it was indeed a point of inflection. Whew. All right. These take a while, don't they? All right, let's do example 6. Hopefully it won't be quite as long. All right, sketching the graph of a trigonometric function. Analyze and sketch the graph of f of x Were there any questions? I forgot. I erased it. I was so tired of it. No questions. Okay. I'm glad I can't reproduce it. Okay. All right. Here's your new function. F of x is equal to cosine x over 1 plus sine x. Okay. Now, this is not a polynomial function. It's a ratio, but it's not a rational function because these are not polynomial functions. These are trig functions. Okay? So, what do we need to do? Okay? Some things we can't do, like you can't talk about end behavior yet, okay, because you don't have ratios. Yeah, you can't do that. But you can talk about your zeros. Where is this equal to 0? What will make that equal 0? The function itself. Okay? Don't worry about the denominators. Okay? The only thing that can make this function 0 is the numerator.
Pi over 2.
Okay, it'll be your half pi. Every half pi. Negative pi over 2, pi over 2. 3 half pi, negative 3. Yeah. Every half pi is going to be a 0. So this will be the zeros for this function are, and they don't give us a limit to it, do they? So it says here, because the function has a period of 2 pi, why is that? Because both sine and cosine have periods of 2 pi. You can restrict the analysis of the graph to any interval of length 2 pi, so they suggest using negative pi halves to 3 halves pi. No real reason for that, but yeah. So we are just going to limit, because it's going to repeat itself after that. So our zeros are going to be, let's just write down a few. As you said, pi halves, 3 halves pi, and we'll do minus pi halves and minus 3 halves pi. Now that is actually 4 pi. We're not going to use all those, but we don't need to go beyond those. Okay. Now, we could evaluate the values there, and I suggest that maybe you should, okay? But those are the x values. This is x equal those values, okay? Sorry, my writing stinks. Now, another thing we can determine from here is what are the things we considered in rational functions? We considered our zeros, we got them. I already said you can't really talk about horizontal asymptotes because you don't have a ratio of leading terms. So we're not going to worry with that. What is another thing we could do? Oh, we could always do our y-intercept. What's true about a y-intercept? Say again? Okay, and where is it located? Y-intercept. Where?
Where it's equal to 0.
Where x is equal to 0. X is equal to 0. Because that's where y is equal to 0, right? Your x-intercept. So the y-intercept is where x is equal to 0. Plug in a 0. What do you get? 0. Really? What's cosine of 0?
1.
All right. And 1 plus what sine of 0?
0.
0. So that'd be 1 over 1, which is 1. So your y-intercept, these are your x-intercept, or your zeros, and your y-intercept, we didn't calculate. The y-intercept is 0, 1. Okay? We got a point on the graph already. Okay? Now, what's another thing we considered for rational functions? Again, we can't say much about horizontal asymptotes because that's the ratio of leading terms. We don't have any leading terms here. Okay? But what do we have? Not horizontal asymptotes. Vertical asymptotes. What makes a vertical asymptote?
where it's equal to a 0 in the bottom.
That is exactly. You can't have a 0 in the denominator. Ever. So therefore, that's going to be a vertical asymptote, a place where x cannot live. So what makes that denominator 0? In other words, 1 plus sine x, I can't write, it cannot equal 0. How can you solve that inequality? Second, okay, subtract 1 from both sides, and you have sine x cannot equal -1. And where did you say that was? 3 halves pi. So x cannot equal 3 pi over 2. And that was one of the places we, whoa! Problem, Houston. It was a potential 0, but it's also a a vertical asymptote where it looked like it would be. Okay, who's going to win that one? We'll have to see. What's that?
Should be the asymptote, shouldn't it?
Yeah, I think it will be. Okay, I know at least it's going to be a whole function. It can't be there. Okay, it cannot be there. Okay. So I think you can't talk about end behavior either because this is repeating, so it doesn't have any real end behavior. But is there any other place where that would be true? X equal -1. Sine x cannot equal -1. We're sort of centering ourselves on 0, right? So it can't equal -1 at negative pi halves. There it would be, see, sine x is like this, right? So it's a -1 over here at minus pi halves, and over here at 3 halves pi. Okay? So there is another place, 3 halves pi, negative pi halves, which is also one of your potential zeros, okay? And I agree with Clark. You almost have to say the vertical asymptotes win here, okay? So you got vertical asymptotes there with zeros at the others, okay? At pi halves and at -3 halves pi, okay? So, now, they did not choose well, okay? In fact, you really do need to graph a little bit beyond what they said here. Well, maybe not really, okay? Okay. Now, let's look at some of the features here. What's the domain of this function? All real numbers except 3 halves pi or -pi halves plus 2n pi. Okay, whichever of those you choose to start with plus 2n pi, because these are exactly 2n pi apart. So that does define one interval 1 period. Okay, so between those two, that'll work. Okay. Okay, your range of the function, as you're approaching either one of these, you're either going to positive infinity or negative infinity. So basically, your range is all real numbers. Okay, the period is 2 pi because the period of the numerator and denominator are both 2 pi. The x-intercept, the only one we have that makes sense here is pi halves. Sure, -3 halves pi is again, but that's the next period. Okay, so in that interval from -pi halves to 3 halves pi, you have just 1 0. X-intercept sorry, pi halves 0, and then we already determined our y-intercept was 0, 1. vertical asymptotes are where it's not defined. At 3 has pi at negative pi halves, and every interval after that, 2 pi from that. Horizontal asymptotes, none. Symmetry, none. First derivative. Oh, we didn't do that. I was avoiding that because it's a quotient root. No, okay. So what is our first derivative? F prime of x. How are we going to do that? 1 plus sine x times, I think I'm going to have to erase some stuff here, so let me go on and do, we've already solved this, so I'm going to wipe this out. All we needed to know were those things, okay? Times what? Which what? Rule. Oh, what have we got here? What's that horizontal line called? Things are written next to each other in parentheses. What are you doing? Multiply. If they're like this, you're dividing. What's the answer in a division problem? Oh, second grade. Maybe kindergarten. What's the answer in a division problem? Quotient. So guess what kind of rule we use? Quotient rule, of course, okay? And that's what we're doing. Low, 1 plus sine x, right? And what's the next part? Still waiting for it. Derivative of cosine, which is? Negative sine, you got it, okay? Then what? Minus cosine x times cosine x. Very good. D high. I mean D low. Low, high, D low. Okay, over 1 plus sine x squared. Okay? Now, let's see what we got here. We got a minus sine x minus sine squared x minus cosine squared x, right? Agreed or not? Agreed, okay. All over 1 plus sine x squared, okay? Now, I'm going to rewrite that numerator slightly. Minus sine x minus a sine x, if I factor out a minus, sine squared x, sorry about that, plus cosine squared x. Isn't that right? Yay or nay? Okay. And that's over 1 plus sine x squared, right?
So how did the first sine x go from 1 plus sine x to negative sine x?
Okay. What's the question? What did I do there? Magic. No. It was 1 times negative sine x is negative sine x. Sine x times negative sine x is negative sine squared x. And then minus cosine squared x. Right? It was distributing, but the distributor was on the right rather than on the left. It looked weird, but it's still true. So what does that give us? I'm really stretching this out. Since we have two minuses here, let's just factor that out, a minus, and that first will be a sine x. And what's sine squared x plus cosine squared x? I'm going to fire your trig teacher. Okay. Huh? It's a 1. You're absolutely right. That'd be 1 plus sine x plus 1 over 1 plus sine x squared. Well, guess what? Sine x plus 1 is the same as 1 plus sine x, so that goes out, and you basically have negative 1 over 1 plus sine x. There's your first derivative. Okay? Now, what are we interested in here with your first derivative? Why do we take it anyway? Except it's a Cal 1 class. You always take the first derivative. Good answer, right? Okay, now, why do we take it? What does the first derivative tell you? Critical numbers. Okay? And where do they exist? Where either the first derivative is 0 or where it's undefined. Is that first derivative ever 0? Remember what determines the first derivative? I mean, whether it's a 0 or not? The numerator. Is negative 1 ever 0? Not in this universe, okay? It can't be, okay? So therefore, there are no places where the first derivative is 0. Are there any places where the first derivative doesn't exist? Yes, where that denominator is 0, and we've already done that. That was the same denominator as here, so that's at your half pies, okay? So the values that we are interested in are your, well, we know you got vertical asymptotes at negative pi halves and 3 halves pi. So sure, yeah, there are no, those are not critical values. That the function doesn't exist there, nothing exists there, okay? So the only one in this interval that will count will be your pi halves, which happen to be okay. That would be your 0 as well, and that's also where the first derivative is 0. So not only is it 0, the function is a horizontal tangent there too. No, I'm sorry. A vertical tangent there, because the first derivative doesn't exist there, okay? So that's going to be a little funky, okay? So keep that in mind. Critical value would be x equal pi halves. See, what does this book call them? Critical numbers, critical values? Huh? Numbers, okay. Critical number, x equal pi halves. You have one at the other two as well, but you know the function doesn't exist there, so it can't be, that's the only one that really grabs our interest here, okay? Now, what else might we decide to do? Oh, a second derivative. Now, I'm going to rewrite that first derivative a little bit differently. I'm going to rewrite it as 1 or minus 1 plus sine x to the minus 1. I don't know if that's going to make it a little better, but I think it will. I mean, otherwise we do a quotient rule with a 1, and that's a little bizarre. Let's just do it that way and see what we get. So what would be f double prime? Get out of there. Say again? Okay, this is a power rule. Minus 1 times minus 1 is 1 times 1 plus sine x to the, a little louder? Nope. Negative 2. You drop it by 1. But then we have a chain rule situation here, times really? Derivative of the sine? Cosine, not negative cosine, cosine. Cosine x. Which, now I can write this as, I don't know if this is helpful or not, cosine x over 1 plus sine x squared. Okay? Now, what are we interested in here? Where that is. Oh, well, what does second derivative tell us anyway? Yeah, possible inflection points. And where do they exist? Where either that is 0 or doesn't exist. Guess what? We're right back where we started with. It's 0 at pi halves, at negative pi halves, and 3 halves pi. Okay? At negative pi halves and 3 halves pi, the function doesn't exist. Okay? So don't make the critical value there. Don't make a point of inflection there. Sure, it changes its concavity, or may, but I mean, it's not even connected there. So I think we're right back to pi halves. Okay? So, where were we here? Okay? Oh, wrong page. Yeah, I'm on the right page. Okay, we had already stepped down through here. First derivative was negative 1 over 1 plus sine x. Second derivative was cosine x. Yeah, there it is. Cosine x over 1 plus sine x squared. Critical numbers, none. Okay? Possible point of inflection, and I would have sworn we had a critical number at pi halves, because the first derivative didn't exist there. Okay? Why are they not counting that a critical number? Maybe they evaluated it and saw that it wasn't going to work. I don't know. Okay? And possible points of inflection pi halves, and sure enough, that does turn out to be 1. Your concave down, and then, concave up and then concave down by the figure, but we haven't done the figure yet. But critical numbers, no, that's the one that sort of bugs me here. Okay? It certainly is one to consider. Okay? But why do they reject it? Okay? Well, let's start at the x equals negative pi halves. We know there f of x is undefined, f prime of x is undefined, f double prime of x is undefined. That's a vertical asymptote. Okay? No doubt about it. Okay? From negative pi halves until pi halves. Okay? Your first derivative, your function, from negative pi halves to pi halves. Okay, negative pi halves, the function is 0 over 1, so it's 0. No. 0 over 0, which is undefined, vertical asymptote. Sorry about that. Okay? And then let's go to pi halves. That's your possible critical number, but let's see what happens there. There, your function value is at pi halves. This is 0. This now becomes 2. So 0 over 2 is 0. So there, sure enough, you have, and that is your x-intercept. Pi halves, and we didn't evaluate it till now, pi halves 0. Okay? Now, your first derivative there is undefined. Okay? But that doesn't stop it from being a critical value. I don't see why it isn't. its value there is 0. Now, what kept it from being that, if you go to the left of that, the first derivative is negative. And if you go to the right of it, it's still negative. Okay? So therefore, it's crossing the x-axis. It doesn't have a change of value there. So you don't have that's what negates it from being a critical value. The function itself is positive on the left, negative on the right, I think. Yeah. That was from, wait, let me back off from that a second here. We're at pi halves. At pi halves, cosine, before pi halves, cosine is positive, and sine is positive, so yeah, it's positive on the left of pi halves. To the right of pi halves, cosine is negative, but sine is still positive. 1 plus sine is still positive, so that's negative. So it was positive on the left, negative on the right. It can't be it's not a critical value. I mean, it's one to consider, but it wasn't one. So that's why they ignored it, okay? They didn't break it down, I think, as well as they should have here. I think they should have done negative pi halves to, yeah, no, that's right, negative pi halves to 0. The function is positive. The first derivative is negative, going down all the way. And the second derivative, oh, we didn't do that one. Where was our second derivative? Right here. Between negative pi halves and pi halves, the cosine is positive everywhere there, and 1 plus sine, whatever that is when you square it, that's going to be positive. Okay? Wherever it is, it's going to be positive. Okay. So that's positive everywhere, meaning it's concave up everywhere from negative pi halves to pi halves. And if you look at the graph, you'll see it's concave up there. When you reach pi halves, your function is 0. That is a 0. We found that. Okay? That's a 0, yeah. The first derivative is negative. There's the first derivative right here. Yeah, when sine is pi halves, that's 1. This is negative. So that's what keeps it from being a critical number. At pi halves, oh, I'm sorry. This wasn't a critical value. X equals pi halves. Pi halves sine is defined. That's a 1. So that's 1, negative 1 half there. Sorry, that was not a critical. They were right. I was wrong. I was still, this is not a critical number. I was thinking that was a place where you had an undefined first derivative. That first derivative is undefined at 3 halves pi, okay? Because 3 halves pi, not at pi halves. At 3, okay, so this is still undefined. The function's undefined, first derivative is undefined, second derivative is undefined. Everything's undefined there, so those are not. But at pi halves, it is defined, but it's not 0. Okay. Sorry, I messed that up. Okay. And second derivative is positive. Okay. Okay, let's move from pi halves to 3 halves pi. And in that range, your function is, your numerator is negative, and your denominator is positive, okay? Yeah. So therefore, the function is negative there. Your first derivative down there is negative everywhere, or in that interval anyway. And then the second derivative is positive. No, negative too, because cosine is from negative pi halves to, for pi halves to 3 halves pi, the cosine is negative, the denominator is positive, so that's negative 2. Okay, so you notice you did have a change of sign of your second derivative at pi halves, so that was indeed a point of inflection, and then everything's undefined beyond. So there's your graph. One y-intercept, one x-intercept per period, and then vertical asymptotes define your period, can define the period. Decreasing everywhere, changes concavity, so it has a point of inflection. All right. Okay. Let's look at your homework exercises here in 3.6. And again, I said this before. Do all of 5 through 8. You'll find the answers for 5 and 7 in the back. But do them all. They're well worth it to do. Okay? Do any of the odds 9 through 35. They're all at calcchat.com. 33s at calcview.com. Do any of the odds 37 to 43. They're all at calcchat. 37s at calcview. Do any of the odds 45 to 49. They're all at calcchat. None of those are at calcview. Do 51. It's at calcchat. Do either 53 or 55. They're both at calcchat. 53 is at calcview. Do 57. Or at least give it a shot, and give 59 a shot, and then look at 61 or 63. Then do either 65 or 67. Do 69, and all these odds are at calcchat. And then we did slant asymptotes, if you remember, so do any of the odds 71 to 75. They're at calcchat, not all at calcview. Try 77. It's a bit of an involved problem there, but give it a look, see if you are interested at all in it. Then there's a think about it, either 79 or 81. And then true false, either 83 or 85. And I think, again, all these should be at calcchat. 87 is a graphical reasoning, as is 89, so do either of those or both if you choose. And another slant asymptote problem is at 91. It says anyway. 93 is an investigation type problem, so if you're interested in that, go for it. All right, I wish we had time to do optimization research. Did any of you determine you need this in your future major? I know if you're going to be an industrial engineer, you probably need it. Are any of you heading that way? You might need it in your other majors too, but I say let's, for the sake of time, we need to skip 3.7 and move on to 3.8. 3.8 should be fairly simple and straightforward, so let's give it a look. Okay. I wish I hit the wrong key. I wish I had time. Nope, that's not it either. That's the key I should hit. Sorry. Okay. I wish I had time just for a slideshow of 3.7, but I think we're running pretty short on time for that too. So let's move on to 3.8. Newton's method, and is this the last? Oh no, we need to do differentials too. Wow. Okay. Okay, continuing in chapter 3, application of differentiation. There's a lot of them, aren't there? Okay. Well, this is Newton's method. Okay. This guy who invented calculus, he came up with a way of finding zeros that nobody has improved on since he invented it. You would think they'd come up with something better. It's approximating zero of a function using Newton's method. The technique for approximating the real zeros of a function is called Newton's method. It uses the tangent lines to approximate the graph of the function near its x-intercepts. Okay? Basically, this is what you calculate. Any of you have a graphing calculator? You don't. Nobody, huh? On that, you can tell it to find the zero of a function. How does it do it? Newton's method, okay? It's the best going, okay? To see how Newton's methods work, consider a function f that is continuous on an interval a to b. You can't have any gaps, otherwise it drives it crazy. Differentiable on the interval a to b, which may not include the inputs, but on anything within that. If f of a and f of b differ in sign, then by the intermediate value theorem, f must have at least one zero between a and b. So here we have a function. It's got to be continuous on a to b, and it has to be differentiable on a to b, and it must, f of a and f of b must differ in sign. Okay? So, to estimate the zero, here you have the function a to b. Continuous function in between there. Differentiable in between there is smooth, that makes it differentiable. And f of a is positive, f of b is negative. Alright, so we're okay with it. So to estimate the zero, choose an x1 that's somewhere between a and b. Doesn't matter where it is, just somewhere between a and b. They chose one. Okay? And then they evaluate that function at x1, f of x1. Okay? You have that. Okay? Newton's method is based on the assumption that the graph of f and the tangent line there both cross the x-axis at close to the same point. Okay? Well, the graph comes down here, the tangent line crosses here. Now, if this tangent line crosses somewhere beyond b, you're sunk. Choose another x1. Okay? And you'll see you're sunk. Okay? It doesn't give you an answer. Get something closer to so here's your c, and here's your x2, where the tangent line crosses. Okay? What you do then, they're going to do it on the next page, I think. No, they're not. Because you can easily calculate the x-intercept for the tangent line, okay, you can use it as the second and usually better estimate of the zero of f. Okay? So your first estimate was this x1. Now you've got this. That's better. It's closer to your actual one. Okay? So guess what you do? You go down and do alpha of x2. It's down here. Do a tangent line here. It's going to get you here. Then do this one. It does a tangent line. It gets you there. And so in no time, you zoomed right into C. That's what's happening. I wish they showed it all in the same graph, but they didn't. Okay?
You said that if your tangent line comes down before C, that's when it's bad?
If it comes down outside of B, okay, let's say it got really flat up here, and you chose that as a thing, and your tangent line is somewhere there. Okay, then choose better. Okay, choose an x1 closer. That didn't work for you. Choose a different one. And after a while, you'll get one that works. Okay, most of the time they'll work pretty close to any type. The only thing you watch for are horizontal tangents. They will never cross. Okay, so throw those out. Okay, because you can easily calculate the x-intercept. We already did that. The tangent line passes through the point x1, alpha of x1, and has a slope of f prime at x1. The point slope form, use the equation of the tangent line, would be y minus alpha of x1, that's y minus y1, okay? It's equal to the slope times x minus x1. Y is equal to slope times x minus x1 plus alpha of x1, okay? So that gives you your new guess for the, now all those things are calculable, and letting y equal 0, in other words, your your x-intercept for that tangent line would give you that. Okay? So from the initial estimate, x1, you obtain a new estimate, x1 minus f of x1 over f prime of x1. That's exactly what you get there. Okay? That's your new estimate. And you keep using that, then you do x2 minus f of x2 over f prime of x2. So just calculate your f of x2 and f prime of x2, and that gives you an x3. And you keep doing until you zoom in on something and you get within as close a proximity as you want to it. Oh, here's the picture that shows that. So the first one gave you this, the second one gave you that. I pointed that out to you. Then you go up here, you come here, see, it gets closer and closer to C. Keep doing it until you get there. Okay? Now, you can improve on x2, calculate yet the third estimate. There, again, it's always your previous number minus the f of x2 divided by f prime of x2. Repeated application is Newton's method. Okay. Oh, yeah, we did. Is it? Yeah. Yeah, it's already out of the time. We'll pick up next time on this at the bottom. Nothing new, no new homework here. We have just a few examples here. It's a very short section. And then we'll deal with differentials, and then we're through, I think. Yes. We'll
Test on chapter 3.
Huh?
Then test on chapter 3.
Yeah, test on chapter 3. Right. Okay. So we'll finish Newton's method next time, I think. Not nearly as long as curve estimating, and sketching and stuff like that. Good deal. Have a good weekend. It seems so